we are extremely fortunate to have Professor Jana Tumova visiting us today from KTH, Royal Institute of Technology in Stockholm, Sweden, although she's actually flying straight from the United Kingdom because she is currently visiting Oxford for a year during Christmas. To give you a bit of background on Jana, she got her PhD at Messiah University and was an instructional fellow with the Access Fellowship or KTH for the time, and she also was a visiting researcher at MIT, Boston University, and the Singapore and IC Alliance, which I just learned about today. Well, I'll read your bio. I'm very curious how much you end up showing for that. But anyway, during all of this journey, Jana has been building a really exciting research agenda around how to remake autonomous systems behave in ways that are reliable and specifiable by their designers and by their users in terms of straight requirements using formal methods, temporal logic, and control theory. And so it's very exciting to have us here and tell us a little about some of the work she's been doing on making sure not only that robots end up doing the thing what they're supposed to do, but also that they're able to do so in a way that is socially compatible with humans, coordinated between lawful agents, and ultimately in a way that is transparent and understandable to people. I'll just very briefly say that there's been a number of the awards and honors in that, and prestigious grants that have been supported Jana's work. And there's a couple of highlights. She has the Swedish Research Council's Starry Grant, which is roughly the Swedish equivalent of the NSA Career Award for work on volcanoes, money or default budget go, and a WAS Expeditions grant for her work on socially acceptable robot decision. So anyway, again, thank you so much, Anna, for coming, all the way across the pond to talk to us today, and we're excited to have you here. You go ahead.
Thank you so much. Thank you, Hema. It's impressive that you remember all of those details. And it's always interesting to hear those things about yourself. Mildly uncomfortable here. So thanks for the kind interaction. Thanks for having me here. Hi. I will be talking about from spatio-temporal specifications to robust robot behavior as an overview of themes related to specifications, formal methods-inspired ways to achieve those specifications, and hopefully there will be also some fun robot videos for you in there. So stick with me through the math, and there will be a reward. So starts from spatio-temporal specification. So let's talk about specification. Specification is a way to tell a robot what they're supposed to do or not supposed to do. So what's your favorite way to tell a robot what they are supposed to do? Maybe you like to say, this is a safe set. I want my robot to be safe. I want it to stay within a safe set S. And safe set S is highly rigorous. We can really define it as a subset of our state space. It's not so expressive. It's just a set. We can go further. We can say maybe I like reach avoid. So I will have some goals that I want to achieve, and I want, while achieving those goals, I want to stay in the safe set. Mildly more expressive, still very rigorous. Or I can have natural language. In natural language, I can say something like, robot, help me. And it's really expressive. You want the robot to help you, so you want the robot to do a lot of things. But what it's supposed to do is really hidden behind that natural language specification. It's not that rigorous. There are many ways to interpret such a thing. So what I like working with as a specification language is Signal Temporal Logic specification. It's highly rigorous. It has syntax, it has semantics, it's a logical formalism, but it's a bit more expressive than reach avoid. And I know that a lot of you here might have their own favorite specifications for formalisms, PDDLs, and strips that in terms of expressiveness might be quite orthogonal to Signal Temporal Logic. We will talk about Signal Temporal Logic for one reason, because it's very convenient to talk not only about system state at a particular moment, but about how the system evolves over time. So this is STL, and this is where the math kicks in. So STL, it's a logic, so it starts with a formula. I will be formulating the specification as a logical formula, and I will be building it from predicates. So the predicate will be, I'm going to take my system at time x, system state at time x, at time t. There is a function h. I'm comparing the value of that function h of system state at time t to 0. And this is either true or false. Okay? So that's the predicate. It's either true or false, whether some value is greater or equal than 0. For example, if I take two robots, I may be interested in something like this. This might be my predicate, which is really equivalent to this, and this is probably much easier to read. I'm just interested in whether the distance between those two robots is smaller or equal than some kind of epsilon, which might be interested in maybe because I want to keep them close enough to be able to communicate. Okay? So this is my predicate, true or false. And then I have temporal operators, and this is the thing that takes the predicates and starts evaluating them over time. So I have until. Until says that something needs to hold until something else needs to start holding. And the interval AB here says that this has to hold within A and B. So until is a little bit, it's generous, it's general, but it's a little bit less intuitive than two derived operators that is always or globally and in future eventually. Always is pretty much telling you that within interval A and B, phi 1 has to hold. So I can say things like these two robots within time 0 to 15, they should stay close enough to each other. And then eventually says this needs to happen eventually. At some time point between A and B, something needs to start holding happen. You can also see those without the intervals, and that pretty much means that it doesn't matter where it happens. And this is all the temporal operators that you need to have full STL, to have full expressions in Signal Temporal Logic. So for example, this is that the two robots should come close enough between 4 and 5 seconds, and you can start nesting them. And this is saying always eventually between 0 to 15, they need to come close enough. And that is pretty much equivalent to saying every 15 seconds from the last time they met, they need to meet again. So you can start nesting them and creating a little bit more expressive and interesting properties that you might want to have from your robotic system. And then you can take classical Boolean operators like conjunction, disjunction, and negation, and just start connecting those temporal operators and nested temporal operators into more complex things like, okay, always the robots should be far enough from each other, but close enough to each other. And then maybe robot number 1 needs to reach region A sometimes every 5 seconds. And robot number 2 needs to reach region B sometimes every 10 seconds. Things like this. So then this specifies how your two robots should behave in space. what we have is really planning with STL constraints now. So STL is a specification language. What we would like to achieve is some kind of robot behavior, path or trajectory, such that we are minimizing some objective. We respect our dynamics, we have our inputs, we have our free space that we are staying in. And then on top of this, we have the STL formula. So the black part you might have seen millions of times. The blue part is new one for us here today. And we have tons of techniques to deal with this. We have automata-based techniques. So automata-based techniques would take the STL formula and basically try to distill how logically different modes of the system switch. So you would take the STL formula, you would translate it into an automaton, which is a discrete structure with basically nodes and edges. It's very similar to state transition system. And once you do that, you would work with abstraction, discrete abstraction of the dynamical system to compose them together into something that we call product. In that product, you would capture the behavior that is allowed by the system and that is allowed by the STL formula captured through the automaton. And then you would analyze this and get something out of it in terms of control strategies in the discrete space that provably satisfy the STL formula. That's one way to go. You can have multiple game-based approaches. So when you are in multi-agent settings or you have some sources of uncertainty, these automata-based techniques would take a form of game-based techniques. You would start treating it a little bit like a game of on graph. There are also some other game-based techniques. You could go sampling-based motion planning. You could view it as a sampling-based motion planning problem where you are trying to do the usual A to B with some STL specification on top of that. So you would do something like RRTs or PRMs or RRGs and equip it either with the automaton to capture a specification or something else, and we will look into that a little bit. You can treat this as trajectory optimization problem. Just already looks like that, like a candidate to swap it into some sort of mixed integer formulations, right? You could go all the way, for instance, to control barrier functions and different kind of closed loop synthesis approaches to find feedback controller that satisfies STL specification. So the community developed very many different approaches to this type of problem. All of them are suitable for a little bit different situation, depending on what you're interested in, depending on what you're interested in terms of dynamics of the system, what you're interested in terms of what you want from the system, how much compute you have available, and so on. There are also data-driven approaches, and I will not be talking about them at all today, but there is reinforcement learning with STL constraints, where you try to flip STL into reward structure, for instance. You can also go with some deep learning, and that's a whole field on its own. So we have options. So we have options how to address this problem. And once again, STL comes as a constraint here. So it can be satisfied or not. One thing that you can do with STL as well is that STL itself, it doesn't have to be yes or no. It can be to an extent. So if I have two robots that are satisfying my STL specification, they are behaving exactly as we told them to behave, they're meeting and they're going away and so on. Well, some of those behaviors you would say like, oh, if something goes wrong, they actually have better chance to still satisfy the specification. This just looks a little bit more robust. If I have a specification like something should happen within 5 seconds and it happens within 2 instead of within 5, then I might feel like this was a little bit better behavior, right? It happened earlier. I wanted it to happen within 5 seconds, but it happened earlier, so it feels better. So is there a way to look at STL not from yes or no perspective, but STL from optimization perspective? And the answer is yes, there is a notion of robustness. It's called that way. It's called robustness, but it's a little bit different robustness that you might know if you have, for instance, control theory background. So let's take a look at example. I have here 3 different trajectories or paths of a robot that was given a goal to reach a goal within 1 second and to stay at least 1 meter from an obstacle at all times. That's it. It's reachable, but it's STL. Here I have a path. It took it 1.1 second, but it kind of like stayed quite far enough. Then I have 0.9 seconds. It stayed medium far enough. And then I have one that is like going very close to the obstacle, but it's very fast. My question is, which one is the best? How can we measure that? We can measure that through looking at temporal robustness, the right time robustness. This is a number that's expressing to me how much could I have shifted the trajectory in time and still satisfy the STL formula. So this would be sort of here in this situation, how fast, how much kind of like slack I have left. So here, I was too slow. I should have been 0.1 faster to satisfy this part of specification. Here, I was fast enough, and I also have some reserve. I have 0.1 reserve. I could have been slower, and I could have been way slower here, so 0.5. So this is robustness. And according to this robustness, this trajectory is the best. It has the highest value. An alternative is looking at spatial robustness. So spatial robustness is telling me how much am I respecting the values that I require from the predicates. So intuitively here I traveled 1.5 away from the obstacle. I only require that this will be 1. So I could have gone closer. I have positive robustness here, 0.5. And here, this was 1.1. So I could have gone closer by 0.1. And here I went way too close, and that is why my robustness is negative. This is violating the STL specification. So I have 2 different viewpoints, from temporal viewpoint, time robustness viewpoint, and I have spatial robustness viewpoint. Each of them giving me a little bit different feeling of what's better and what's worse. I can also maybe combine them together and weigh them. And there I have yet another robustness, sort of like taking into account both. So now I can not only put STL as a constraint, I can also make it a part of my optimization function. And then I can either decide to keep this part, or I can decide that I don't need it. So this, when I require this, I will be looking for solutions that have positive robustness. If I don't find one, I'm going to report a solution that satisfies STL formula does not exist. If I remove that constraint, I will be also looking for violating solutions, which might be handy if you don't want your robot to just stop and say abort mission. So sometimes we are fine with violating STL specifications, especially if they don't represent something safety critical, more preference based, and then we can afford to remove that requirement. And again, we have a range of techniques that were investigated to address the problem where STL robustness is a part of my optimization function. This time, the automata-based one that I discussed before, it's not going to be working that well it just doesn't translate that well. Same control barrier functions. There's not so much work yet out there on these type of problems, but the other ones, there is some work out there, and especially on sampling based and motion planning and trajectory optimization. It comes into the framework very naturally, and I'm going to show you how. So, least violating or maximally satisfying RT star. I hope you are familiar with what RT star is. It's a motion planning algorithm that tries to get you from A to B. So from some start to some target. It builds incrementally a weighted tree, and then as it goes, it reconnects the tree. It incrementally updates the shortest path that it has based on the distance you traveled. And eventually, what it gets is asymptotically optimal path. We took the STL and put it into RT star. We still have some weighted tree. It may have a little bit more dimensions because we want to keep track of logical switches that we have in the STL, but those are technical details. And instead of incrementally updating shortest path, we are incrementally updating the maximally robust path according to the robustness metrics so that we optimize for some other cost function, for a cost function that includes the robustness. And when you design the cost function right, it actually works and it maintains the properties of RT star, meaning that you have asymptotically optimal, asymptotically most robust solutions with respect to your STL specification. So maybe I could show one fun project where we use this. So this is a project where we looked into aligning safety as defined mathematically with safety as perceived by people. So this is the expedition project that Jaime mentioned in the beginning. So basically, the story is that I have a colleague next door, Yolanda Leite. She's a social roboticist, and we started talking about safety and what it means, and then we realized that very often people perceive safety differently than there is actually safety in the system mathematically. So there is a lot of time they trust the system more than they should or less than they should. And it doesn't really help to tell them, here is a control barrier function, you can trust the system. So we started looking into what we can learn about how people and robots should work around each other. And we started with a project that is called Game of Chicken. You have a person and a robot going opposite each other. And the idea is that one of them needs to swerve, otherwise they bump into each other. It's called Game of Chicken because there is a little bit reward if you don't swerve, and there is a lot of negative reward if you bump into the robot. So the question is really who chickens out and goes away. We collected a bunch of interesting observations from there, and it became a very typical user study HRI paper. We learned things like that people swerve farther away from PR2 than Sophie because Sophie looks more human-like, so they feel that they can be closer maybe. People swerved more with the teleoperated robot. So if we tell them this is teleoperated robot versus this is autonomous robot, they just swerve more with the teleoperated robot because maybe they don't feel like they have to be so polite, right? If the robot is autonomous. And then people behave more politely, meaning that they also swerve more with what they thought were other people. So basically those were the insights, but what came out as well, it was a data set of these trajectories. We had a lot of these trajectories and we thought maybe we can apply some STL inference or develop some STL inference algorithms to get descriptions of typical human trajectories around the robot. We got those. We put it together with STL RT star, and we took the real-time version that is able to handle dynamic obstacles. And again, we were asymptotically maximizing adherence to these descriptions of the human behavior. And what we were hoping to get is, loosely speaking, moving more like a human would around a human. And then we implemented it in the lab and tried, treating a human like a pure dynamic obstacle and treating a human like, then implementing in the robot the behavior that we inferred that this is how the human would behave. And then the result is that the robot was perceived as more intelligent, more predictable, and having more social competence. This is the results of the user study. So in this case, STL came in as sort of like preference. We wished we kind of infused it into a working social navigation system to achieve behavior that was more human-like. That was one fun project, and we used pure spatial robustness there. And but spatial robustness is maybe not always the right thing to do. The whole difficulty about this formulation and about looking at the optimization of STL robustness is that we need to pick optimization function, contains the robustness, but really corresponds to our interest, and then also allows for some provable guarantees when we plug it into a planning algorithm, and also does not come with prohibitive computational complexity. So this is like the balance between what we want, what we can do, and what we achieve. That's a big question, Ani.
That's the question about the previous.
Absolutely.
So I guess do we just qualitatively? Sure. Yeah. Do we qualitatively the trajectory on the left actually looks more natural, like just the vanilla RT star?
That one, yeah.
And the one on the right seems like it's kind of more hesitant. Like it goes to swerve one way, comes back, goes again. So I guess what is it about, just qualitatively, about the behavior on the right that seems more natural?
Is that that the robot took a little bigger detour around the human.
Okay. But it comes back, right? So
it sort of, it clearly goes out of the way. We did not ask about these things. Okay. We did not perform that kind of interview, but it kind of, when you observe it is true. This one looks very natural. It just goes as close to the human as possible, because that's you want shortest path. This one takes a clear detour. It may feel, maybe my hypothesis may feel more polite, or may feel like it's deliberately getting out of your way. But here what you see is, of course, a little bit of delayed effect of the real-time RT star. This is a lot of unoptimized implementation that you are seeing that's doing this.
Okay. Maybe just one more quick question. I'm curious, like how much of, I guess how much of the power of STL is needed here? Like, could you get away with something much more heuristic and yeah?
You could. The point of STL is really the universality, right? It's, yes, we could take a look at it as like social navigation problem, going from A to B on the same path. And if I treat it as a problem, I would probably find better fitting solutions to the problem. The point was that this is sort of like general framework. If I come to a different society, or come to maybe multi-agent system, every time I collect a new data set, I will have a way, I will not have to automatic way to synthesize those types of controls. I will not have to manually fine-tune some social navigation system. So it's kind of like a little bit of generality is the point of STL here. Thank you. More questions?
Like you to jail. You got my picture for the video.
Hi. I'm just curious about whether or not you have considered using what I might call a quantitative version of temporal logic. So if you have a property P1 and you have a property P2, and you have some cost to violating those properties or some distance from a goal, and you have each of those properties separately, I think you don't really want a Boolean conjunction. You want to view each of those properties as, having a cost, and then you want some, as you showed in an earlier slide, like a weighted combination.
Yes.
And so I just wonder if you want everywhere, not Boolean operations, but weighted combinations of operations, or maybe that doesn't make sense, but I just wondered if you want to comment on that.
It does make sense. It makes perfect sense. And I have seen recent works looking exactly into kind of like these things, how to prioritize different parts of STL specifications with putting the weights as a part of syntax. You could also try to do that, and then it will kick into the semantics and it will kick into the framework as well. It's a very natural idea, for sure. Yeah. All right. So, so we are at a point where we are discussing what's difficult about this. And one of the things is to decide what you actually want to optimize for. So, so maybe here, do you drive like that or do you drive like that? Which one do you prefer? That's fast. And that's kind of like safer in terms of keeping enough spatial distances. So now, when we were trying to think about how do I put in rules of the road as STL specifications into some driving framework, because that's the thing that will keep us safe on the roads, right? So we thought about how do we design the optimization function. What are we doing? Are we optimizing for spatial robustness or temporal robustness, or should I combine them together? And when combining together, you still need to keep in mind that RT star maybe will need some properties of those functions so that it can maintain the asymptotic optimality. So basically what we end up with very quickly is that we take the trajectory length and then the violation cost. The violation cost is the time robustness, the spatial robustness with some weight. And then in the weight, we chose two parameters that are user specified. And those two parameters would be alpha and A. Alpha is basically a hard constraint that's telling you with your spatial robustness, you do not want to go below a certain threshold. And A is telling you the rate of how fast you start caring when the spatial robustness starts degrading with respect to the time. So it was just an idea to trigger different kind of different. If I choose different parameters to trigger different kind of behaviors, it turns out that I have to make some sacrifices in the syntax there. So I have to have some goal that can happen in finite time, and I have to have a fragment of STL that doesn't really nest the formulas so that I could plug it into RT star and keep my nice RT star properties. But that was enough to capture what we want from autonomous driving. That is a goal. And in our case, we looked into responsibility sensitive safety. So you want to keep safe distance, you want to keep safe overtaking, and rules of responsibility sensitive safety, like 3-second rule, can be encoded into STL, and we are not the only ones who tried to do this. So now we have some, say, rules of how to behave on the roads in STL, and if we choose different parameters, values of parameters A and alpha, what we get to is different behaviors on the roads. We get defensive, neutral, or aggressive drivers, and where we define the parameters differently, these are the different behaviors we were getting, and they were actually evaluated as defensive, neutral, and aggressive by human participants. So what I was trying to say till now is basically that there is a few challenges around planning with STL specifications, when it comes to expressivity, computational feasibility, and the fitness to the problem. I would like to look into trajectory optimization techniques as well a little bit. And with trajectory optimization, I would say that two main directions is to treat STL in mixed integer programming framework and treat it in nonlinear programming framework. So in mixed integer programming, you turn STL robustness recursively, because you have nesting, into mixed integer constraints, and then you create either a MILP or mixed integer quadratic program and solve those. These are really good. They work with linear constraint, they work with convex constraint. They start struggling with scalability as usual. Or you can go with nonlinear programming, but if you want to use the power of gradient-based optimization solvers here, you need to flip the STL semantics so that it becomes smooth. Otherwise, it's a lot of min and max operations. So there are smooth approximations that you can use, and then you can use these powerful tools. But by that, you're losing a little bit of the exactness, a little bit of the precision. So here is when you are losing a little bit on the guarantees by using the approximation. So those are two general directions. There are also SMT-based formulations and so on. And this is just looking into open loop, into trajectory optimization. There's a really nice review from some years ago that also looks into closed loop. Well, so one fun project that I want to show where we use this trajectory optimization formulation is this free-floating transportation. So my student Joris, we have been working on a space robotics project, building space robotics lab at KTH, and really looking into how to control and plan for robots in space. And what we wanted to do is transport objects in space. So your STL formula would look like you have a bunch of specifications for the objects, you have a bunch of specifications for the robots. In space, objects float. So you don't have to grab something, hold on to it, and carry it somewhere else. Instead, you can bump it, send it somewhere, and then bump it again and send it somewhere else. So basically, the idea was, let's transport object in space by impact. Okay, great. So the first thing that we do is we use some impact model. So we are doing model-based techniques. We would like to use some trajectory optimization. And we are asking when, how, and with whom to impact. To make the problem tractable, we use Bezier parameterizations, and then we reformulate it as MILP. Works, right? Sort of does. So it needs a little bit of time to make up its mind, and now it sends the robot to the goal. So eventually the robot, which is actually the passive object, this is not actuated, goes into the goal, and the other one stops it. Okay? Except that the challenge that is really difficult is that all models are wrong, right? Especially in space, the model that is wrong is the impact model. So the impact model actually has some sort of plus minus delta, and then in our physical platform, this is what kicks in. So now our question was, is it still correct to think about robustness as satisfaction of some spatial properties, or should we think about robustness in terms of the impact error? The robustness turned into maximal admissible uncertainty under the impact equation now. So that is what we want to optimize for. And we follow basically the same scheme. And the difference that you will see is that when there is uncertainty, the robots behave a little bit differently. They need to be a little bit more proactive there. So that's a part. That's one part. And now that we are very robust to the error in impact, we realize that, well, that's fine, that's nice, those are our guarantees, but then we actually need to implement it on the platform, and we need to follow with executing it. So we have impact-aware MPC, and then replanner, and then low-level allocation to actually make it work on the platform. So we had nice guarantees here in terms of robustness with respect to impact, to satisfy our STL specifications. And then basically on this lower level, we do the best we can locally to make that happen. And it works. So this is how it looks like actually on the Space Robotics platform. So you want to go to these 3 regions and eventually end up here. This is the passive object that was pushed around by the robots, and that's it. And that's it. It worked. So a little bit more in general terms, if we think about models not being correct, if we have a disturbed system, these model agnostic robustness metrics that we know from classical STL, like spatial and temporal robustness, do not really consider dynamics of the robot and dynamics of the environment. And we need to account for those, especially for systems like that are subject to a lot of disturbances. So if we take such systems, and here I have an underwater system that is subject to some currents, the spatial robustness for this formula that tries to send your robot to stay the robot in region A between 4 and 5 seconds, and then come to this final region exactly at time 15. In spatial robustness, it would look like this. But what you actually want to have is this behavior. This is the behavior that is most robust with respect to disturbance. This is the planned trajectory for the disturbance is not there at all. And this is the worst case one. Still works. So the question now is flipping into what is the maximum admissible disturbance that the system can tolerate so that the specification is still satisfied. And we address it by decomposing it into subformulas and then running backward reachability computation for each of the subformulas. So this is quite general approach to systems under disturbances. It is adequately computationally challenging, and for instance, compared to the impact, in the impact dynamics, we had a little bit more idea about what's going on, and it was computationally much easier to tackle. All right. So that is because all models are wrong, but that is not the only source of uncertainty that we have in general. So generally, we would like to account for uncertainty in broader sense. For instance, yet another source of uncertainty could be in observations. So this is for robots that we don't quite know where we are. And here, we would particularly like to distinguish between behavior like this and like this. So in here, I have a UAV, tries to avoid this dangerous location. And this behavior is just fine. But this behavior where the robot localizes itself through the GPS antenna is a little bit better. And we would like to acknowledge that in the robustness that we are trying to optimize. Maybe the robustness should be somehow related to the risk that the robot crashes into the dangerous area. And that is where STL has been extended with probability and risk. So STL under stochastic uncertainty, what we have here is uncertainty presented in form of some external random variable. And then our predicates are reflecting that in measuring probability that the value of the predicate of the function is greater or equal than 0 and comparing it to some gamma. So before we had this, no random variables, and now we are including the probability in there. So we can have chance predicates, or we can go one step further and have risk predicates when we take an appropriate risk metric. And then, using temporal operators and Boolean operators, suddenly we have a mechanism to reason about systems that have stochastic uncertainty. So in our case, what we had was we assumed Gaussian parameterization under of the underlying probability distributions and used extended Kalman filter. So I have belief that is defined by a matrix and its covariance, right? And the risk predicate, what we did is we flipped them into the belief space. So suddenly I have risk predicates in belief space, and my optimization problem is now defined in terms of belief space. So I'm trying to maximize the spatial robustness, but using these belief state risk predicates. And when I use NLP with smooth approximations, it will start giving us some nice results. Like for instance, here you can see how optimizing for risk looks like versus chance constraints. And this ball here shows the uncertainty. So the robot can be anywhere here, and you see that it's just like right touching the obstacles. So if I optimize for chance constraints, yes, the probability that the robot will crash into the obstacles is still bounded very well. But when I look at risk and include both sort of the severity of the robot's actions that it shouldn't do and the probability, it gives you a little bit safer behavior. And finally, imagine that you have your robot that starts here, this belief state at time 0, and you want to get into you want to stay within region G3 until the uncertainty is sufficiently low. Then you also want to reach G4, and whenever the uncertainty is above the threshold, you want to move slowly. So you're reasoning about how much uncertainty there is actually. And this is what came out when we put it into the trajectory optimization framework. Start with belief 0, and then the robot proactively goes and gathers some information to know a bit more about where it is. So this is light-dark domain. Wherever there is light, the robot can localize itself better. And then when it knew a lot about itself, it starts speeding up. So the closer the circles are, the slower the robot goes. So it did exactly what we hoped it would do. So we have some framework to deal with uncertainty. Well, takeaways from today. First, what I believe is that if you don't have a rigorous specification, you don't have a proper understanding of what the robots are doing, how well they are doing it, you don't have a way to evaluate robot behavior. STL, it's a powerful rigorous specification language. You can use it for preferences, you can use it for safety constraints, you can use it for spatio-temporal properties. You can also use it with different kind of robustness metrics to achieve some optimal behaviors. It can be viewed as a constraint and or optimization function. There are different adaptations of syntax and semantics to match our systems and interests, including uncertainty. And sometimes we can get some guarantees. So at least something. So if we hold on to and really wish for provable guarantees for systems like robots in physical world, this is very far-fetched. So we have to give up a little bit of that here and there. It is all kind of combination of richness of model and specification that we can handle, the strength of guarantees that we can get, and the computational feasibility of the methods that are dealing with those specifications and models. I did not talk at all about data-driven planning and control, which is a challenge on its own. I did not talk at all about how to design STL specification, which is a really big topic today. There are papers showing that, for instance, they call STL suspiciously tricky logic, I think. And the only difference between non-experts and experts in success of designing STL specification is just that the experts believe themselves a little bit more and are more confident about the results. So designing STL specification by a human is still a tricky topic. And now that we have LLMs, there is tons of papers from past year or two that translate natural language to some sort of temporal logic specifications. Some of them are trying to do that now with tools like conformal prediction to kind of give some guarantees on the translation as well, which is really interesting line of work. And one challenge that I see is also dealing with hard to formalize objective. In other words, designing the specification in general, knowing what I want from the system. If I say I want a robot to be socially capable, how are you gonna specify that so that you can evaluate that? So that's it. Thank you so much for listening, and thanks to my group and my students for chipping in, and the funding bodies for funding our research. Thank you so much.
Wonderful. Thank you so much, Jana, for the great talk. And now we have a few minutes for questions. 5 minutes or so. So let's see who wants to break the ice and jump in with the first one.
Thank you for the wonderful talk. I have a basic question about STLs. So is it possible to say something about the relationship between X's over time? Like, I never want to exceed some, distance over time, but not say specifically anything about like xt and xt plus 5. It seems like the predicates are always about like a single time step.
I am not sure. I might have seen some sort of parametric STL where the A and B are parameters depending on... Have you seen anything on that?
Is a question sort of in aggregate over time as opposed to at any given time step?
Right. Something that only is about like a relationship between two times in the future. Not a statement about just a single time step. So one example might be like, there must exist some position that you have to revisit many times in the future, but we're not saying which position.
That one, I personally haven't seen that one in our community. I am sure that there might be something in sort of like formal methods community that dig deeper into these languages and specification languages, logics, and things like that, and develop a variety of things. It's a great idea.
Cool. This is pertaining to Professor Silver's comment. I was wondering if the reach void formulation we saw earlier could count as a way to basically keep some sort of time constraint without specifying time step. Like, does that count as what you were asking about, or is that like a different question?
Okay.
Yeah.
For reach or void, it seems like you need to specify the exact states, kind of as a set, like a set of states you're reaching and a set of states you're void. So I was wondering, without saying which state, could you say there's some state that I'm going to revisit, many times in the future, but I don't care which state.
Like existential quantification or something like that. Yeah.
Okay.
Haven't seen it, but I might find that paper and then I'm going to send it to you.
Yeah, I suppose this is also on that theme, I suppose. So temporal logic was invented so that people could avoid having to explicitly talk about particular times, T1, T2, T3 in their formula. So you have these quantifiers that implicitly talk about the times. And so you've used, in choosing temporal logic, time becomes a really first-class entity in your specifications. And so I was just wondering, because space is also, it seems extremely important in your specifications. I just wondered if you had considered some other kind of logic in which your location is similarly a first-class entity supported by logical connectives that hide some of the details about how the space that you're in is manipulated. Again, with analogy to temporal logic, also hiding details about how time is manipulated.
There have been some efforts on that, including we have a paper from, I think, 3 years ago where we define spatial operators like left off, right off. So that, so we did that. I can share that paper. It came out in Autonomous Robot. I think that it's called spatial something. So the logic that we propose there is called spatial. In the end of the day, I have to say that it's just syntactic sugar, right? The operators, the left of, right of, on top of, it can be expressed in STL because it's so powerful, but it just becomes convenient to talk about where I want to put my objects, for instance, in robot manipulation. So we have looked a little bit into that as well.
But I mean, temporal logic is also just temporal logic is also just syntactic sugar at some way it could translate it to first order logic.
Great. So maybe I'll jump in with a question if no one wants to come in front. Something that you had touched on earlier in the discussion is ways to aggregate multiple constraints or multiple properties that we might want to either enforce or favor, sort of combine their different robustnesses with different weights, or even think about them probabilistically and then talk about the probability that a certain predicate is satisfied at any given time. And sort of following up on some questions that had come up earlier, what are better and worse ways of doing that aggregation? Because it seems, for example, talking about probabilities, if you take a probabilistic assessment on a particular predicate, and then you put that, but that's just for one particular time step, and then you put that inside of an STL specification saying, for example, at all times, something, it's not the same thing to say that at all times the probability of the constraint being satisfied is greater than 0.9 than to say that the probability of the constraint always being satisfied is greater than 0.9. And so I'm curious, probably a similar thing happens when you're doing, summing things over time. What are the right ways to do this?
There is no better and worse. Right? This is multi-objective problem. So you want to have a logic that supports what you want to achieve, but at the same time, you need to be able to support it with the tools to be able to evaluate, monitor, synthesize, verify, falsify, whatever you're interested in doing with the logic. So if we talk about the probabilities in particular, there is probabilistic version of LTL. It just takes LTL, which is simplified version of STL. You basically have predicates. You don't have the exact time constraints. So it just talks about ordering of events. There's a probabilistic version of that. You can very simply take MDP with that and do value iteration and get bounds on satisfaction of your LTL formulas. And it works, but it doesn't give you this reasoning about uncertainty on kind of like the predicate level. There is really cool work by Yanis Kantaros on planning in kind of like uncertain semantic maps, where he has predicates that you see something and you are even not sure if that's the thing that you see. So there is like a bunch of different ways that you can approach this. Different people approach this differently, very often motivated by the domain that you're looking at. So I think the answer is it's better if it's better fits your domain and you can still deal with it. Generic, sorry. Not better. It's not going to get better.
No, it's very fair. Let's see. I feel like somebody should ask a question about the human side of things. I'm actually very curious to learn, to get a sense of how do people, especially experts, interact with these systems and specify. I realize that we actually have gone a little bit over. Maybe to finish with one open-ended question: what do you think is the most challenging aspect of getting people to understand these temporal logic specs or to work with them?
No idea, honestly. I think that the syntax and semantics, the moment that you start nesting formulas, the moment that you start defining your predicate functions, it just becomes messy. So I think that after years in the business, I can take a look at STL formula. I can know what I kind of understand what it is meant to say. But I think that we do need tools that will bridge this exact gap, the natural language to STL. But how to do that in sort of to keep the provable essence there, to keep the guarantees, that's a really, really big question. But it's not natural and as it is.
Right.
Yeah.
Awesome. Well, thanks so much, Jana. Let's thank our speaker one more time.
Thank you.